So as we continue our study of integration, it's important to remember the graphical representation of what a definite integral actually is. Specifically, this video is going to show you how to take that idea that a definite integral is really the area between the function curve and the x-axis. And we're going to look at different ways to find or compute that area, but not so much algebraically, for example, with an antiderivative or the fundamental theorem of calculus. In this video, what I'd like to do is present to you a way to figure out a geometric interpretation to definite integrals. And here's an example of a graph, and there's 5 corresponding definite integrals that are asking you to evaluate them. Notice the directions. The graph of f consists of 2 straight lines and a semicircle. Whenever your calculus directions get that specific and they tell you that you're looking at a picture that is linear, or there's a quarter circle or a semicircle as part of the function, there's probably some underlying need to find the area. So think about the area of a circle. Think about how we might find the area of a triangle, or the area of a trapezoid or a rectangle within some sort of function, or between a function and the x-axis. Using formulas for geometric shapes and their corresponding areas can help us evaluate definite integrals. And so in this video, I'd like to walk through these 5 examples, and then I'll end with one additional example to help you out. So the first one says, find the definite integral from 0 to 2 of f. And again, here's my function f. And what I've done is I've actually shaded, there's 3 separate regions when I look at this. I see sort of a triangular region at the beginning from 0 to 2. I colored that in, and I actually computed the area of that using 1/2 height times base, 1/2 base times height, the area of a right triangle. And I found that to be 4. So there's 4 square units in that triangle. And notice that region is entirely above the x-axis. Then I have this yellow colored semicircle. It's below the x-axis, so the sign of the definite integral will take on a negative value. I computed that. Area of a semicircle would be 1/2 pi r squared. It appears that the radius is 3. So 1/2 pi times 9 would give me 9 pi over 2, but because it's negative, because it goes below the x-axis, we're going to make that a negative value for the definite integral. Finally, there's 1/3 triangle there that has an area of 2. It's positive because it is above the x-axis. So number 1, find the value of the definite integral from 0 to 2. Again, that's simply going to equal 4. I used my knowledge of geometry and applied 1/2 base times height, the area of that right triangle, to get my solution. The next integral is from 2 all the way to 8. Notice that that encompasses the entire semicircle. But again, the answer, even though the area of that semicircle is positive 9 pi over 2, because of the location of the semicircle, of the area, of the region on the graph being below the x-axis, that definite integral actually takes on a negative sign. We're going from 2 to 8, positive widths, positive delta x's, but I have negative heights, so negative 9 pi over 2. Now, look at number 3. The integral goes from 8 to 5. The bounds are backwards, but if you start at 8 and travel left to 5, that would essentially entail negative widths and then also negative heights. So there's going to be a double negative happening within the integral computation here. If you switch the bounds, because we're used to having that lower bound be on the bottom of the integral sign, then we'll have the integral from 5 to 8, but make sure we add the negative because that action negates the value of the definite integral. So for number 3, we have a positive value of 9 pi over 4. That's the quarter circle's area from 5 to 8, but again, it's sort of the double negative with negative widths and negative heights. So the overall sign there would be positive. Number 4, the entire region under the curve from 0 to 10. So I'm going to add up the positive area regions, 4 plus 2. I'm going to subtract the 9 pi over 2, so 6 minus 9 pi over 2 would be that value. And then finally, number 5, absolute value of the function. That absolute value is going to reflect any negative piece of the function above the x-axis. So essentially, any negative region will then bounce up and become positive. So 4 plus 2 remains 6, but now I'm going to be adding the 9 pi over 2 to that 6 to get my absolute value function within that integral. Now, I wanted to end with one additional example, and that is an absolute value example. Every now and then, we'll come across on an AP exam or on some sort of review a question that looks something like this. And it may show up on a quiz or a test. One of the things that I want to make sure you know about is when you see absolute value bars, be careful that we don't jump into algebraic rules, but rather always consider using a graphical approach, whether you're taking a derivative or in this case here, whether we're evaluating a definite integral involving absolute value. So the function here is the absolute value of x minus 1. So using my knowledge of functions and transformations, it's simply the absolute value graph shifted to the right by 1 unit. So the vertex is here at 1, 0, and the bounds of the integral go from -5 to 2. So I made the sketch right here. I'm using a graphical approach, a graphical and geometrical approach to find the value of this integral. I marked -5, I marked 2. It's a lot easier with graph paper. And I colored in the region that I'm looking to compute. So the area under the function curve from -5 to 2, notice it consists of 2 triangles. Triangle number 1, 1/2 height times base, and here's a little tiny triangle number 2, so area here is 1/2 times its height and base as well. So if we compute this, I'm going to have on the left here, the height appears to be 6, and its base is also 6. So 18 will be that triangle on the left, and then the tiny little triangle is actually 1/2 of a unit squared. I can confirm that here, 1/2 times 1 times 1, or simply 1/2. So the value of this definite integral will be 18.5. I used a geometric approach. No need to do anything with FTC. I could type it in the calculator to confirm that my answer is right. But knowledge of geometric formulas of shapes from geometry class, like triangles and circles, trapezoids and rectangles, will come in handy when you're looking to evaluate definite integrals. So good luck to you. I hope those examples were helpful, and enjoy the rest of your study on integration.